Good morning, everyone. Hope you had a good weekend and that the quiz 1 results didn't stress you out too much. I wanted to start class with a small announcement regarding that. The results for question 2 sucked, and in many cases, it's not your fault. The grading guide that I gave the markers, I feel in hindsight was too specific for exactly the way that I would do those questions in class. Many of you did use different techniques, equally valid techniques, and lost marks that you shouldn't have lost. So some students have done this already, but if you found a perfectly good value for M, but the marker didn't like it, email me and I'll give the question a second look and probably give you some free marks that you already earned. In future quizzes, I'm going to tell the markers to be more chill. Anywho, this week we're doing more asymptotic notation. Don't quote me on this, just in case I'm misremembering, but I think this is the last week of math stuff. There's of course going to be theory content throughout the entire course because this forms the foundation for the practical stuff that you'll do when you have a real job. But I believe this is the last week of purely doing math stuff. You're actually going to code some stuff soon. Wow. Now recall the hierarchy of functions. This slide is kind of like a summary of the whole week and last week. The next one is too. But we have the desire to sort functions. That's because we have already found cost functions for algorithms, and we want to use those cost functions and tell which algorithms are faster or just less resource intensive than others. So if one algorithm has cost function log some base of n and the other has cost function n squared, you want to know which one's going to perform better in the real world. You already know a lot of this stuff, so I won't dwell on this slide too much, but we wanted to formalize the notion of a function being smaller than another or greater than another, and we did that with big O and big omega, respectively. This week, we're going to sort of formalize the rest of the comparison operators between numbers. You don't have to do this. You haven't seen most of this stuff in the slide yet. So I'm just going to do this. So f of n is n squared times log base 3 of n, and g of n is just n squared. Which of the following are true? I'm not going to go through the definitions for all of these. The proofs would be exhausting, but I will go through the intuition that would sort of guide each. F is in big O of g. That's like saying that I need a thinner pen. What? Whatever. So big O is like saying less than or equal. Big omega is like saying that it's greater than or equal. You all know this much already, and you can probably guess by the fact that the functions have the same degree, like the same highest power of n, but f of n has another non-constant multiplier. F of n should be larger, so b should be true. We see that here too. And now let's take a look at the other notation that you'll be learning this week. F in this symbol big theta is like saying that f of n is equal to g of n. So remember, this isn't an exact comparison. This is just what each piece of notation is sort of like. So a function being in big theta of another function being kind of sort of equal means that they grow at roughly the same rate. So 2n and 3n are in big theta of each other because they're both polynomials of degree 1 and grow linearly. But we'll see more on that later. Little o is like a stronger version of big O. It says, or it's basically like f of n is strictly less than g of n. And finally, little omega, it's like saying f of n is strictly greater than g of n. I think the idea of a function being less than or greater than is pretty intuitive, and the notion of functions being equal, even though they're clearly not, is less intuitive. But hopefully it'll become clearer with some more definitions. More of these. Do we need to do this? I don't think this is very useful without knowing what little o really is. Okay. Big theta, equality. Yes?
Are you posting these?
Pardon me?
Are you going to post these?
Yeah, definitely, after this class. I'm aware that I don't have the, pardon me? No problem. Yeah, I'm aware that I don't have this nor the readings on UMLearn. I'm gonna post the slides right now. I was gonna do it after class, but like, it's nice to have these. You guys can talk or do whatever while I'm uploading this. I appreciate how quiet you're being, but like, I'm kind of wasting your time right now. Okay, it's up. And I'll post associated readings soon, but this slide should be sufficient to learn these bits of notation that we're going over right now. Anyway, big theta. What does it mean for two functions to be equal to one another? Well, in the wacky world of inequalities, we use this idea of functions being equal if the function can be bounded between two constant multiples of another function. It's pretty similar to the definitions of big O and big omega, except you sort of do both. Big O said that there existed a constant m such that f of n is less than or equal to m times g of n. And we have those two elements here. Likewise, big omega said that there existed another constant multiple such that f of n is greater than that times g of n. And we have that here. So I'm going to just doodle a bit. What do I want to demonstrate this with? I'm going to say that n plus 1 is in big theta of n. A nice and simple example. So here's n plus 1. And per the definition, we're going to find two constant multiples of the other function, n, such that the thing we're trying to show is in big theta of the other thing, f, in our case n plus 1, is bounded in between those two constant multiples forever. So I'm pretty sure just the constant multiples 1 and 2 will work. So I've shown here informally, don't do this on an assignment, this is not a proof, that clearly n plus 1 after a certain point is greater than 1 times n and less than 2 times n. So because of that, we say that n plus 1 and n grow at the same rate. They're equal. And now I want to show that, or show off a pair of functions that aren't equal. N squared is not in big theta of n. This hopefully makes some sense already based on the hierarchy of functions. It said that n squared grows faster than n, so clearly it doesn't grow at the same rate. So let's semi-formalize this. So we got n squared. And then we're going to attempt to bound it between two constant multiples of n. Bounding it below is simple enough. I just set m1 to 1, and then, yeah, obviously n squared is bigger than that. Now, I wonder if I should do this on Desmos. That'd be fun. Nah, I don't feel like figuring that out live. You'll just have to take my word for it, and I encourage you to play around with stuff like this in Desmos or any other graphing calculator. But we can try to find an M2 such that M2n is greater than n squared after some point, but it turns out it's impossible. So I don't know, like this might look like 10 n, but n squared is just going to keep growing faster and faster and eventually overtake it. We could do like m2 equals 1,000,000 and get a graph that looks like a straight line. This graph hypothetically is very zoomed out, but n squared will overtake it anyway. For all constant multiples m, or m2 specifically here, for any constant multiples, n squared will always eventually become greater than n times that constant multiple and stay that way. So let's do an example. This one's kind of fun because the rough work won't be that intense. You can kind of just eyeball this. The solution is totally spoiling our values of m1 and m2, but I'll still show you how we got there. We want to find m1 and m2 such that we want to make this whole inequality true. In other words, m1n is less than 5n plus 1, and 5n plus 1 is less than m2n. So what should we do to m1? Well, the expressions already look pretty similar. We could guess that maybe 5 would work, and then it is immediate that, like, obviously 5n is less than or equal to 5n plus 1. There's a plus 1 on the bigger side, and they're otherwise identical. So this goes to show that when you're finding values of m, you can, a lot of the time, just guess and check. And if you find something that works, it works. You only have to employ the more complicated mathematical techniques from the other slides if guessing and checking doesn't work, which it often won't, so it's good to know the techniques. But this example is nice and simple. Now we want to find m2. We want to make it so 5n plus 1 is less than or equal to m2 times n. And like before, the expressions already look very similar. So we can just guess. Maybe it's 6. And upon further analysis, this actually more closely resembles what we did in our rough work. This is the rounding up trick, we see that 5n plus 1 must be less than 5n plus n under the assumption that n is greater than 1. So now we have the inequality we want. 5n plus 1 is less than 6n. And along the way, we had to assume that n is greater than 1. So in our formal proof, we just say that. N naught, we set to 1. And recall from the definition that the inequality has to work for all n greater than n naught. As such, setting n naught to 1 ensures that n is greater than 1. And then you sort of just walk through the inequality that you just found. So that's it for that example. Now we're going to show that two functions don't grow at the same rate. This is a formalization of a similar argument to what we saw here. We were able to bound n squared below by a constant multiple of n, but we weren't able to bound it above. Likewise, in the negation of the definition of big theta, we have an or statement. In this case, it's saying that either M1 doesn't do its job, it doesn't provide a lower bound for f of n, or M2 doesn't do its job, it doesn't provide an upper bound for f of n. Only one of these has to be true. In this case, n to the power of 3 is going to be greater than in big omega and small omega, but that doesn't matter yet. It's going to be bigger than 7n squared plus 1. That is, it will be possible to find a good lower bound for it, constant multiple of g of n, but it won't be possible to find a upper bound for it. As such, we only have to find an n greater than n naught such that that side of the or statement is true. Because the way or statements work, if one side is true, then the whole thing is true. So even though this is not true for all M1, that is, it is possible to find an M1 that's a good lower bound, it doesn't matter because the other side is true. This will work for all M2, and thus the entire or statement will work for all M1 and M2. Oh. The text on the bottom of this slide sort of sums up what I was saying. We can show that n cubed is eventually larger or smaller than 7n squared plus 1. We know intuitively by the hierarchy that n cubed is strictly larger. So we're going to focus on finding an n that makes the greater than inequality true. So what exactly are we trying to show? From here, the work that we do to get a value for n looks a lot like what we would do in rough work for other definitions, specifically big omega. We have two sides of an inequality. We want to solve for n. It's not really feasible right now because one of the sides has multiple terms. So we want to find a new expression, sort of in between the two sides of the inequality. That's easier to compare with the other side. So it sure would be nice if that constant term were actually n squared. So let's say n squared has to be greater than 1, perchance. Wait. And then we can simplify this, much simplified. So now we have the expression 8m2, 8m2n squared. That is less than m2 times 7n squared plus 1. So if we can show that that is less than the original small side, original big side, n to the power of 3, then we've shown that the entire inequality is true. Luckily, solving for n in this case is real easy. We're just going to divide both sides by n squared. Bada bing, bada boom. Now we've found a value of n such that, or rather a lower bound for n, that makes the inequality true. Now we just have to show it in our formal proof. It's the usual routine. Make sure to pay attention to quantifiers when you're doing questions like these. Whether the formal statement says like for all m, or there exists an m, or for all n, whatever, that will determine what you're solving for. So in this case, we have any m1 and m2, any n naught. There exists an n, so we solved for n in terms of m2. We choose n equal to maximum of n naught and 8m plus 2 plus 1, or 8m2, all that, plus 1. For reasons that are hopefully familiar, but it's good to repeat these kinds of things. We found in our rough work that n has to be greater than 8m2. So we have that here. We have, from our definition, that n has to be greater than n naught for any n naught greater than 0. So we have another constraint. In order to ensure that n is greater than both of these, we just say it's greater than, or it's equal to whatever the largest of the two is, plus 1. Then we have everything we need to show that the inequality is true. Note that we already, I guess that should say n greater than 1, but whatever. Note that we also found that n is greater than 1, but we didn't include it in our max function input because we're already adding 1 to it, and since both of the things involved in the max are greater than 0, something greater than 0 plus 1 is going to be greater than 1. So it's sort of implicit in our choice of n. Regardless, we point out that it's greater than 1 because we're going to because we did that rounding up trick of turning a 1 into an n squared. Then, sort of the rough work in reverse. Since n is greater than 1, and thus n squared is greater than 1, we can change 1 to n squared in the inequality, add and simplify to get 8m2 n squared. And then since n is greater than 8m2, we turn 8m2 into n, multiply them together to get n cubed, and we have our inequality. We've shown that for all of these wacky numbers, there exists an n such that some dumb stuff we don't care about, or f of n is greater than m2 g of n. Remember, it's an or statement. Only one of them has to be true all the time for the entire or statement to be true. Hello? What the heck? Is the rest of this lecture just a featureless void? Dang. Well, I don't want to cancel class, but let me do some debugging. Oh, true. There. Oh, these are new? Okay, that's the one we just did. So I guess we gained back 2 slides and we'll worry about the rest later. Works for me. More complicated example of the same idea. We're going to show that 3 to the power of n is not in big theta of 6 to the power of n minus 5 to the power of n. Notice how the hierarchy of functions went. Actually, I'm not going to talk about that yet. We don't know, or we know from the fact that we're told to prove this, that 3 to the n doesn't grow at the same rate as 6 to the n minus 5 to the n, but we don't know whether it grows more quickly or more slowly. So we negate the definition of big theta again. For all m1, m2, and n naught, there exists n such that either m1 g of n is greater than f of n, or f of n is greater than m2 g of n. The first step to proving that a function is not in big theta of another is to figure out whether you're going to prove one side that that a lower bound doesn't exist. Wait. Yeah, that a lower bound always exists. Hold up, I'm confusing myself with inequality symbols again. Okay, so you have to choose whether you know that a lower bound doesn't exist or an upper bound doesn't exist. In this case, it might be tempting to see like 6 minus 5, that equals 1, that's less than 3, so 3 must be greater. Please don't do that. The asymptotic growth of a function, that is where it sits on the hierarchy, depends entirely on what the largest term of the function is. So 6 to the n is huge. 5 to the n is also quite huge. You might think that subtracting 5 to the n from 6 to the n makes the result less than 3 to the n, but that 6 to the n is absolutely humongous, and we're looking at how they behave from n naught up to infinity. 6 to the n will eventually overtake both 3 to the n and 5 to the n. After a certain point, this whole difference will always be greater than that. Subtracting 5 to the n is not enough to make 6 to the n small. So that was my intuitive explanation. That would sort of be my thought process. That's a big number, such that it's big. So now that I strongly suspect that this side is larger, that is, there doesn't exist a constant multiple such that m times 3 of n is greater than this difference, I'm going to prove, this one, I think. These inequality signs trip me up so often, it's crazy. They'll probably trip you up, but double check your work, triple check it, quadruple check it, and you'll probably be fine. In my case, I have an advantage because the solutions are written right here. Looks like I was right in my guess because the first step of the proof says that we're going to do the inequality with m1. So no matter what m you choose, 3 to the n will always eventually be less than 6 to the n minus 5 to the n. Same old song and dance. We have two sides of an inequality. One of them is hard to compare to the other because it has multiple terms. We're going to try and simplify it into an expression that sits between the two sides of the inequality, and then compare those and solve for n. Even though this sort of looks different from previous examples because we're dealing with exponential functions, not polynomials, we can use a very similar technique, namely the factoring trick. Previously, we would factor out the highest power of n. Now we're going to factor out the highest base of n. Still works. So we factored out 6 to the n, and we have that. We're going to simplify a little bit. And now we have the perfect opportunity to simplify this. If we set n greater than 1, then 5 to the 6th times n is going to be at most 5 to the 6th. And then since we also subtracted, the inequality sign flips again. And our result is that we get that this is greater than n1 times 6n 1 minus 5 over 6. I should have. Technically, you don't have to. This is rough work that wouldn't be handed in, so like it'll be impossible for the marker to go like, hey, you should have written down n is greater than 1. But you should anyway, in order to keep track of the assumptions you're making and the bounds you'll set in your final proof. So 1 minus 5 over 6 is 1 over 6. Change that to m1 over 6 times 6n. And then we have an expression that looks simpler. Come on, let me zoom out, whatever. m1 over 6 times 6 to the n is probably easier to compare to 3 to the n. But we can't like divide by a power of n or do a logarithm yet. So we're going to do one more little refinement to make this easier to compare. And that's just to split up 6 to the n into 2 to the n times 3 to the n. So now we have our sort of updated inequality. 3 to the n is less than m1 over 6 times 2 to the n times 3 to the n. What am I doing now? Oh yeah. We're going to divide both sides by 3 to the n. Bit better. We're almost able to solve for n by just taking the logarithm base 2 of both sides. before we do that, I'm just going to divide both sides by m1 over 6, so as to move everything that isn't the exponential function over to the other side. And then just raise everything, or sorry, take the base 2 logarithm of everything. And there we have another upper bound, or another lower bound. If n is greater than log 2 of 6 over m1, then the whole inequality should work. Such as the main proof says. Just like before, we say that it's the maximum of the bound we found earlier, log 2, 6 over m1. And not, because n is defined as being greater than n naught, plus 1, which ensures that it's strictly greater than both, and also eliminates the need to put 1, which we found is necessary here, in our max statement. And then it's sort of rough work in reverse yet again. We say that this implies the assumptions that we made earlier, essentially summing up the results of our rough work. And then we start with one side of the inequality, use our bounds and assumptions to get the other side. And is there anything left super notable? Looks like just regular algebra. When you're looking over this on your own, I recommend looking at the final work they do and see what steps of that come from what steps of, in this case, my rough work, but if you're doing this yourself, your rough work. As long as it corresponds to the proof. I don't know if it will. That'll be it for the class. On Wednesday, we're going to look at little o and little omega. See you then.